United States. So it's going to talk about p-adic Julia sets and geometrically finite rational maps. So are you able to share your screen?
Okay, thank you.
Yes.
Let me see. Okay, does it work?
Yeah, perfect. Thank you very much.
Great. Thank you, Matthew. It's okay. I'm really happy to speak here in this virtual conference, virtual workshop. Yes, I was in Chile several months ago, but now, yeah, I just left there. Okay. Anyway, so today I'd like to talk about the recent work on p-adic Julia set and the geometrically finite rational maps. It's a joint work. It's joint with Shirley Fan, Hongming Nie, and Yufei Wang. Okay, so now first let me give the general setting. So let's consider two metric space, x low and x1 low 1, and consider a family f of maps from x into x1. Okay, let me see. So the fact is that there is a maximum open subset of x on which f is equicontinuous. Okay, I don't know what happens. Okay, so then when the target and the domain are same, so we can consider the iteration of self maps on x. So then we consider family f, which is the nth iteration of a self map f from x to x. Then we can define the photo set, which is the maximum open subset of x on which the family f is equicontinuous. So we denote the photo set by ff. And we also have the Julia set, which is a complement of the photo set. So, okay, so now if there is a subset of x, let's say y, such that f restricted on y is a self map on y, then we can also consider the then for this family f, we can also consider the Julia set and the photo set on y. Okay, so in fact we have two Julia sets and two photo and Julia sets. One is for x, one is for y. Okay, let's say the photo set for the map from x to x, say this is a large photo set, and the corresponding Julia set is a large Julia set. Then if we consider f on y, then we can consider the small Julia set, a small photo set, and small Julia set, which is fyf and gyf. Okay, now the natural question is, if the small Julia set is the restriction of the bigger Julia set, of the larger Julia set. Okay. So, okay, by definition, it's very easy to say that, okay, the small Julia set is contained in the restriction of the large Julia set. Okay, now, but for the reverse inclusion, it's okay, at least to me, okay, I don't think it's easy to see that. Okay, so now this is a general setting. So let's consider some examples. Let's consider examples in complex dynamics. Okay, let's consider the Riemann sphere with the spherical metric and let phi be a non-constant rational map. So then let's suppose the autocoefficients of phi are real. Then we in fact then the phi in fact maps the extended real line to extended real line. So we can consider the Julia set. Okay, the complex Julia set of phi and the real Julia set of phi. Okay. So now let's see particular example. Phi z equal to z square. Then the complex Julia set is a unit circle, and the real Julia set is just 2 points, -1 and 1, because for any real numbers whose orbital value less than 1 will contract to 0, and orbital value the real numbers whose orbital value bigger than 1 will contract to infinity. So then the real Julia set is just 2 points. So now in this example, we have the real Julia set of phi is exactly the restriction of the complex Julia set to the extended real line. Okay, this is a quite an easy example. So now let's consider another example. Let's say this is let's consider phi, which is x squared minus x, which is also a real polynomial. So okay, here is a Julia set. Okay, the boundary of the black region is a Julia set, a complex Julia set. So so the black region is symmetry along the real axis. So we have 0 here. So now we can check that. So all the real points close to 0 will be attracted to 0. So in fact, okay, in this big large black region, so the point will map to the black region on the left, then go back to the middle one, then go to the left. So and eventually convert to 0 on the real line. So okay. So but look, so there is some non-real number x, I mean, which very close to 0, such that under iteration, these points go to infinity. So this means the point 0 is in the complex Julia set, but not in the real Julia set. Okay. So then for this example, so phi x equals to x squared minus x. So we have the restriction of the complex Julia set cannot contain in the real Julia set. Okay. So this phenomenon happens because this point 0, okay, for this example, is a parabolic fixed point. Okay, which this point 0 is fixed and the derivative is a root of unity. So okay, so because this phenomenon, we know these two Julia sets are not the same. Okay, so the existence of such parabolic fixed point or periodic point is an obstruction to obtain the equality between the Julia set. Okay, so in complex dynamics, we don't expect any, I mean, equality. So, but okay, now let's consider the p-adic setting. So okay, let's consider the field QP of the p-adic numbers associated with a natural non-trivial absolute value. That is, okay, each element in QP is a series with coefficients from 0 to, I mean, between 0 and p minus 1, and okay, some order of p. So for any point in QP, we know the absolute value of x is just the p minus k, where k is the least order whose coefficient is non-zero. So okay. So okay, so since this absolute value give us neutral matrixity, which means okay, the sum of 2 points. Okay, okay, sorry, I think that typo. It should be x1 minus x2 absolute value subscript p less than or equal to maximum x1 absolute value of x1 and absolute value of x2 for any 2 points in QP. Okay, so okay, now let's consider a finite extension of QP, and let CP be the completion of algebraic closure of QP. So then on the projective space of CP, we have the spherical metric defined as following. So for any 2 points, we write in the projective coordinate. So then the distance, I mean, of these 2 points is just in this formula. So this means, okay, the projective space of CP is a metric space. Now we can also restrict this metric to the projective space of K. Then we can consider the rational map with coefficients in K. So now we let phi be a non-constant rational maps with coefficients in K. So then we have 2 maps. One is okay, we can regard phi as a self map on the projective space or CP, and we can also regard phi as the self-map on the projective space over K. Then we can consider the Julia set, photo set and Julia set. Okay, we denote by FP1CP phi and JP1CP phi for the photo set and Julia set for the map of phi from projective space over CP to itself. Similarly, we denote by the FP1 K phi and J P1 K phi to be the photo set and Julia set for the map phi from the product space over K to itself. Okay, now we want to say if there's some relations between these two Julia sets. Okay, so first of all, as we mentioned in complex dynamics, there is some special point called the parabolic fixed point or parabolic repeating point, which is an obstruction to obtain the equality. So now in p-adic setting, so we say a periodic point is indifferent if it is periodic and the derivative, multiplier or derivative, so has absolute value 1 in local coordinate. So the case is in p-adic setting, so the ultrametricity implies all indifferent periodic points of F are in photo set. Okay, in the bigger photo set. Okay, this is different from the complex case. So okay, it's not easy, but it's not hard to say this implication. So for example, let's consider the indifferent fixed point. Okay, let's say x0 is an indifferent fixed point of phi. Then near 0 can write phi to be lambda x plus some higher order terms with the value of lambda is 1. Then we consider the iteration of this phi. So we get the nth iteration of phi has form lambda n z plus higher order term. Then now for any 2 point what close to x0, so the distance of the nth image, its forward image, does not increase. Okay, this means this x0 is in photo set. Okay, in the bigger photo set. So now so in non-convection setting, so in p-adic setting, it seems that everything is perfect. So it's reasonable to conjecture that. So for any non-constant rational map phi defined over K, so the small Julia set, JP1K phi is equal to the restriction of the bigger Julia set. Okay. So for degree 1 case, so if phi has degree 1, so we can conjugate by some Mobius transformation with coefficient in QP bar, the algebra closure of QP. Then we have the phi is either x plus 1 or lambda x. So for some lambda in the QP bar. So in the first case, if phi x is x plus 1, then any iteration, then any point will map to infinity, or will convert to infinity. So in the second case, when phi x is lambda x, so we can discuss the upper value of lambda is equal to 1, less than 1, or bigger than 1. So discuss these 3 cases. We can also conclude this conjecture holds for degree 1 case. Okay. Now let's say for higher degree. So let's consider phi is if phi in KZ is a rational map of degree at least 2. Let's denote by critical CP phi the set of credit point in the projective space or CP. Okay, so now a credit point C is valid if P divides the local degree of phi and C. Otherwise, we say the credit point is team. Also, so credit point C is recurrent if it is accumulated by its forward orbit. Okay, we use the notation phi O phi C for the forward orbit. So okay, this is I mean, and this is for the wired credit point. This is quite different from complex settings. Okay, so now for our purpose, we mainly focus on the set of Julia credit points. So we use the following notations. We use the critical CP star phi for the intersection of the credit points and the Julia set, bigger Julia set. Similarly, we use the critical K star phi for the Julia credit point, which lies in the projective space over K. Okay, we mainly work on these two sets of credit points. Okay, so now okay, so for any two credit points, we can define a natural equivalent relation. So let's pick C1, C2 be two credit point. Okay, two Julia credit point. So in projective space or CP, so we say C1 is equivalent to C2 if C1 is in the closure of the forward orbit of C2 and C2 in the closure of the forward orbit of C1. Okay, this relation is an equivalence relation, so we can define the resulting quotient space M phi, just as the critical CP star phi modulo this relation. Okay, in fact, moreover, so the closure of the orbit also give us a partial order on this resulting quotient space. So okay, we say C1 because the class of C1 is less or equal to the class of C2 if and only if the closure of the orbit for the orbit of C1 is contained in the closure of the orbit C2. Okay. So okay, so then this set M phi together with the partial order less or equal to give us give us a partial order set. So we so each list element in this partial order set is a minimal class. Okay, so now for the non-complete setting with finally and one we prove the following. Okay, so let phi be a rational map of degree and these two defined over K. Let's suppose that phi has no variable recurrent credit points in the Julia set intersecting the projective space over K. And and each minimal class in the result in the quotient space has at most two representations in the set critical K star phi. Okay, then we have the small Julia set as a restriction of the bigger Julia set. So okay, I should give some remark on the condition and assumptions on this result. Okay, so the first one is okay, the no variable recurrent credit bond, no variable recurrent Julia credit point. Okay, implies there's no Wandering factor components and has only finitely many period factor components intersecting P1K. This is proved by Benedetto. But I should mention here, our assumption is slightly different from his because we only require phi has no variable recurrent credit point in critical K star. Okay, so in fact, in Benedetto's result, he requires phi has no credit point in critical CP star. Okay, that's slightly different because in our proof we use some weaker result.
So what does the star mean?
Star means intersect with the Julia set in CP.
Oh, I see. Thanks.
Okay, let me go back. Right, star means the intersection with the Julia set.
Okay.
Then the star, okay, critical star, K star is the critical CP star intersect the P1K. Okay.
Thanks.
Okay. So okay, then Juan showed okay there exists rational maps whose coefficient are algebraic over QP and has a widely recurrent Julia credit point. Okay, that is such weird, weird. I mean, weird,
Actually, in QP.
I'm sorry.
In QP.
Oh, in QP. Coefficient. Oh, in QP. Okay, you mean the coefficients are in QP?
Right.
I see. Okay, okay, sorry. Yeah, I thought it was the algebraic over QP.
If
okay,
I
sorry.
remember correctly, it was long ago.
Okay. Okay, so in general, also it's conjectured that any rational maps in KZ has no wandering photo components and has only finite many periodic photo components intersecting P1. P1K. Okay, this is one part. One reason why we use why we assume there's no wandering recurrent Julia credit point. Besides that, we also use this assumption in the following reason. Okay, another reason we need the no wandering recurrent Julia credit points assumption is the scaling property. Okay, so okay, then we say we say phi is locally scaling. Okay, in distance. So on a disk in P1CP, if there is a constant alpha in the valid group of CP such that for all x1, x2 in D, the distance of the image of the 2 points is equal to the alpha of the distance of these 2 points. Okay, so here the scaling maybe not a better word, but here we just mean okay, scaling in distance. Phi itself is not a scaling. Okay, so now let's example for the scaling. So let's suppose x0 is 0 is not a credit point of phi and x0 is fixed by phi. Then near x0 we can consider the Taylor series of phi. So we have this Taylor series of phi. Then we can choose R small enough such that all the terms except the first term in the Taylor series of phi has an orbital value less than the first term. Okay, so even we can choose R small enough such that this equality holds. Then okay, for any 2 points in the disk containing x0 with radian less than radian R. So the distance of the image phi, the distance of phi x1 and phi x2 equals to the derivative, the value of the derivative of phi and x0 times the distance between x1 and x2. Okay, in fact, this small R, from this small R, we have a scaling disk. Okay, so the reason we also use the no weirdly recurrent credit point is the following proposition. So for any credit point in critical CP phi, there exists some R depends on the credit point C, such that for any point X in the disk, I mean containing C with radian R, with X not equal to C, the maximum disk on which phi is scaling is the disk containing X with radian delta phi low delta phi times the distance from X to C, where delta phi is 1 if C is prime and delta phi is P of power minus 1 over P minus 1 less than 1 if C is wild. Okay, so this means okay, if there's no wild recurrent credit point, then we have less control on the ratio of the diameters of internet images of certain disks. Okay, for example, if we consider 2 disks D1 and D2, such that D1 is contained in D2 and both of them close to team credit point. Then under the iteration, under the first iteration, so the ratio of the diameters of the first image of these two disks is the same as the ratio of the diameter of these two disks. Okay. But it's not true, I mean, near the weird credit point. Okay, this is another reason we use the assumption. We use the no weird recurrent Julia credit point assumption. Okay, so now, okay, now let me give another remark on the, sorry. Any question? Okay. So let me give another remark on the minimal classes, because in our main result, we also have assumption on the representations of the minimal classes. Okay, so in fact, okay, the restriction on the numbers of the representation of minimal class implies certain result on the existence of rebellion periodic points. So, for example, okay, let's consider a recurrent critical point C in critical K star. Okay, let's suppose this guy has a unique representation. Okay, okay, I should say the class of C has a unique representation. So because we already assume that no varied recurrent credit point, then this credit point C should be team. So then we have the following result about the existence of rebellion periodic point. Okay, so let's consider the credit point C and point X, which is sufficiently close to C, but it's not a C. Then consider the set, consider the disk in P1K. Okay, such that okay, the DX is the disk in P1K containing X and with diameter low XC here. Okay, here I should say X is in P1K. Now we assume that okay, there exists a smallest integer n such that okay, the nth forward image of dx intersect a credit point, and the covered credit point, I mean covered credit point by the credit point covered by the nth forward image of dx is exactly the original credit point C. Okay, and we also assume so in this orbit from 1 to n. Okay, in this forward image of dx bar from 1 to n, the diameter is not larger, is not too large. In fact, this epsilon 0 is okay, the very sufficiently small number depending on the dynamics of fate. Okay, if these three conditions hold, then the dx contains a rebellion periodic point with period n. So okay, so in fact, okay, if a class has a class of C has two representation, we can also show some similar result about the existence of rebellion period point. But if the class of C has, I mean, at least three representations, then we are not able to show such things. Okay, the big difference is that so if there is only one or two representations, so we know, so for any small disk near the credit point, we consider its image, we know which credit point it covers. Okay, if there are more than I mean, if there are at least 3 credit points, then we cannot control the images of iterations of the iterated image of the disks. Okay, so okay, let's give a sketch of the proof. So okay, in fact, we only need to show one direction. We only need to show the restriction of the bigger Julia, the larger Julia set is contained in the small Julia set. So there are several steps. We first consider the boundary. of the bigger Julia set. The restriction of the bigger Julia set in P1K here should be JP1CP. Okay, here's simple, sorry. So let's first consider the boundary point. So for this boundary point, we can apply the no wandering domain result and the finiteness of the periodic for the component intersecting P1K. We can treat with this boundary. So now, if it's for the interior of this intersection, so we reduce the discussion to the quadratic point in quadratical K star. So in other words, we only focus on the quadratic point. Okay, the quadratic point in quadratical K star. So we can reduce. We can do this because we show that for any P1K disk intersecting the intersection of this intersection have an integrated image either covering a quadratic point in quadratical K star or having a larger diameter. If it has a larger diameter, then we can show this point in quadratical, this point in Julia set. So the difficult part is the case that this integrated image covers a quadratic point. Okay, so now we consider, okay, as long as we reduce our discussion to the quadratic point, so we can consider the equivalence relation on the quadratic point, and then do some argument. It turns out that we only need to focus on the minimal classes. Okay, certain minimal classes. So then, under the restriction of the number of representation and some additional assumption, we show the existence of rebellion periodic points in certain disk. So okay, then to get the conclusion, so we prove by contradiction. So it means that okay, if the small Julia set does not contain the restriction of the bigger the larger Julia set, then we verify the additional assumption in step 4. Then we can get there is rebellion periodic points, which give us a contradiction. Okay, this is the sketch of the proof. So I should remark here that so the no wild recurrent quadratic points assumption, we use this assumption in all steps, but we only use the restriction on the representations of minimal classes in last step. Okay. So, I mean, it would be good, very good to show, okay, this assumption 2 can be removed. So, okay. But we don't know how to do that. Okay, so this is the result about the Julia set. Now, let's use it to show dynamics, the Julia dynamics for geometrically finite rational maps. Okay, so, oh, sorry. Okay, so we consider a rational map in Kx of degree and least 2, such that each quadratic point in the quadratical K star has finite fold orbit. So we say such phi is geometrically finite. Okay, in fact, this means the quadratic point in the small Julia set has finite orbit. Okay. So Right. This okay. This is about the geometrically finite rational map satisfies the assumptions in the main theorem, which means okay, there's no phi has no recurrent critical point because all the critical point in critical K star phi has finite orbit, so it has no recurrent critical point, and each minimal class has at most one representations. So in critical K star. So in other words, this such phi is an example satisfying our main result. So so then by the main result, we know the small Julia set is the restriction of the large Julia set. Okay. So especially the critical K star is contained in the small Julia set because the K star is the intersection of the critical point and the big Julia set and P1, PK1. So okay, so in particular, this critical set, critical K star is contained in the small Julia set. Okay, now we want to show the dynamics of on the K Julia set of geometrically finite rational map phi. Okay, let's denote the critical K star phi, which is the ground orbit of the critical K star in P1K. Then we know the ground. Okay, then by the main result, we know the ground. This ground orbit is contained in the small Julia set because this set, the critical point, is contained in the small Julia set, and the small Julia set is equal to the intersection of the big large Julia set and P1K. So then we can regard the critical K star as a site in JP1CP phi intersect the intersection of the large Julia set and P1K. Then we can consider the ground kind of orbit. Then we can consider the ground orbit of this of this critical set and consider the point in this ground orbit and P1K. So we in fact have this inclusion. The ground orbit of critical K star is contained in the small Julia set. Okay, now we said the IK phi is just the complement of this ground orbit in small Julia set. Okay, so then we show that for any for geometrically finite rational map phi of degree and least 2, then there exists a countable state Markov shift sigma a sigmas and a bijection H from the small Julia set to sigma A, such that away from the ground orbit of critical point, it is topologically conjugate. Okay. Okay, so right. So okay, let's say let me do some remark here. So if the critical point, the critical K star is empty, then it's a special case of called a weak repeller, studied by Fan Liao Wang and Zhou. So in this case, so the phi is conjugated to a subshift of finite type. Okay, but in our case, so if that is a critical point in CK star, so then the Julia set is not explained. So then we may need a countably many states to describe the dynamics. Okay, so I don't want to go to the details of the proof. So, but I just want to say here that to obtain the states, we need to. Okay, we first consider the scaling disks because we know near each credit point, there is a scaling disk. So in fact, by the local compactness of K, so we can know, so for any point in P1K away from credit point, so we can find such scaling disk. Okay, as long as we have such a scaling disk, then we need to decompose this scaling disk such that the image of each resulting disk is a union of other disks. Okay, so this is the main idea to construct such states. Okay, so now let me give an example. So for this result, so let's consider the polynomial from P1Q2 to P1Q2 defined by fx equals to 9/4 x times x minus 1 square. Okay, so in fact, I think Ingram consider the cubic polynomial with rational coefficients acting on product space over C or complex product space. I think he proved that there are only seven canonical classes of such cubic polynomial. A PCF, so post-quadratic finite. So then we consider this example. So in fact, this F is one of his class. Okay, acting on product space over C. So, but if we because the coefficient is rational, so we can consider it acting on QP for any P. So it's easy to check that. So this is the only example in his 7 classes such that this F has a Julia credit point. Okay, so we consider this example. Now since the infinity is a super attracting and totally invariant fixed point of F, which means the inverse of infinity, the preimage of infinity under F is also infinity itself. So then we can only focus on Q. So it's easy to find out the fixed point of F is 0 and 1/3, and the credit point is 1 and 1/3. It means and we can also check that 0 is a rebellion fixed point, and the 1/3 is a super attracting fixed point. So we also have the orbit of the credit point 1 mapped to 0, then 0 is fixed. Okay. So because 0 is a rebellion fixed point, so 0 is in Julia set. Then in turn, the point 1 is also in Julia set. Okay, so now in fact we can check that each credit point 1 or 1/3 has finite orbit, because 1 mapped to 0 and 0 is fixed, and 1/3 maps to itself. Okay, in fact F is post-quadratic finite, and hence it's geometrically finite. So then for this example, we consider the disks in Q2. So the disks AN and AN prime is the ones close to 1, because 1 is a fixed point. So the BN and BN primes are the ones close to 1. So in fact we consider the countably many disks. Here all the disks are in Q2. So we consider countably many such disks near 1 and consider its image, then it maps to disks near 0. Okay, so we consider such disks, then we have the orbit of these disks. So for example, the A prime will maps to an prime maps to an minus 1 prime, then maps to A2 prime, and A2 prime maps to A1 prime, and A1 prime maps to B1, and B1 prime then maps to A1. So similarly, AN will maps to AN minus 1. Okay, because 0 is a Riemann fixed point. So for any small disks close to 0, then it will map to some disks slightly far from 0. Okay, some large disk. So okay, and then eventually, so this small disk AN, which is close to 0 and maps to a slightly larger one to A minus 1, then go on and maps to a larger one A2, and then maps to A1. Then A1 maps to all things, almost all things. Okay, we maps to 1 and a union of BI and BI prime, where I is at least 2. Okay, so we have this orbit. So and all the Bn and Bn prime are okay. Bn and Bn prime are the image of An. Okay, so now we have this orbit for this balls. Okay, I should mention here that so the union of this balls covers the Julia set except 2 points, 1 and 0. Okay, so now we consider the intersection of An intersect. Okay, here should be the Julia set of F in Q2 or in projective space over Q2. So we define the alpha n prime and beta n prime, which are just the intersections of the disks and the Julia set. And then we have 2 more points, 0 and 1. We denoted by alpha infinity and beta infinity. So this gives us the cover of Julia set. So now we let A to be the set of such intersection or such symbols. So then we define a matrix A such that each entry A gamma I gamma J is 1 if gamma J is contained in the image of gamma I, otherwise it's 0. Okay, so now we consider the shift sigma n induced by A. Okay, by this matrix A. So then for each x in the Julia set of F, there is a unique sequence gamma J in sigma A such that the J's interest of X is contained in gamma J. Okay, we call this sequence is the coding sequence, the coda sequence. So this is because this set alpha n prime and beta n prime alpha infinity and beta infinity covers the Julia set. So we can easily find out there is a sequence, and we can show that even that unique such sequence. So now we can define the map from the Julia set to sigma A, such that H sends X to its coding sequence. The point is that so this H in fact is a bijection. This H from the Julia set to sigma A is a bijection. So moreover, if we consider the complement of the ground orbit of 1, remember 1 is the Julia credit point of F. So if we consider the complement of the ground orbit of 1 in the Julia set, so then we in fact have the H is a topological conjugacy between the complement of the ground orbit and its image in the simple space. Okay. Okay, so right, this gives an example, gives a particular example. So right, so let me see. Okay, so I should mention here that in this example we can compute all the scaling ratio of f on each scaling disk. But when we prove the general setting, the general result, we don't need this precise ratio, but we can only prove, abstractly, so by the construction. So okay, so okay, I think I have a little quick. Okay, so I think I stop here. Thank you.
Let's open the microphone and say thank you to Hongming.
Thank you.